Virtual reality, VR, and augmented reality, AR, are two technologies that aim to immerse users in artificial environments, either completely or partially. VR creates a fully artificial environment where users can interact with virtual objects and surroundings. VR typically requires a headset that covers the user's eyes and ears, providing a fully enclosed sensory experience. This allows users to experience immersive environments, such as realistic 3D simulations, games, and simulations. The goal of VR is to create a sense of presence in a virtual environment, so that the user feels like they are actually there. AR, on the other hand, involves overlaying digital information on the real world. This can be achieved using a smartphone camera or specialized AR headset, which allows the user to see a mix of the real and virtual world. AR applications can range from simple enhancements to existing objects, such as a smartphone game that uses the camera to display virtual creatures on a real-world background, to more complex experiences that incorporate digital elements into the real world. Both VR and AR have a wide range of potential applications, ranging from entertainment and gaming, to education and training, to medical and therapeutic purposes. In entertainment, VR and AR allow users to experience new and exciting worlds, from immersive games to virtual tours. In education, VR and AR can be used to create engaging and interactive learning experiences, allowing students to visualize complex concepts and learn in a hands-on way. In medical and therapeutic contexts, VR and AR can be used for exposure therapy, pain management, and physical rehabilitation, among other uses. One of the biggest challenges in developing VR and AR experiences is creating a sense of immersion and interaction that feels natural to the user. This requires sophisticated computer graphics and interaction design, as well as a high degree of precision in tracking the user's movements and reactions. Additionally, VR and AR systems must be able to perform in real time, with low latency and high accuracy, in order to create a smooth and believable experience. Another challenge is the cost and accessibility of VR and AR technology. While prices for VR and AR systems have fallen in recent years, they are still relatively expensive, and may be beyond the reach of many consumers. Additionally, many VR and AR systems require specialized hardware and software, making it difficult for developers to create widely accessible experiences. Despite these challenges, VR and AR are rapidly growing fields, with significant investment from tech companies and governments around the world. As technology continues to advance and costs come down, it is likely that VR and AR will become increasingly accessible and widely used, with applications in a growing number of industries and fields. In conclusion, VR and AR are innovative technologies that offer new and exciting ways to interact with the world around us. Whether it's through fully immersive virtual environments or through the overlay of digital information on the real world, VR and AR have the potential to transform a wide range of industries and fields, from entertainment to education to healthcare. Distributed ledger technology that enables secure, transparent and tamper-proof transactions. It was first introduced as the underlying technology for the digital currency, Bitcoin, and has since been applied to a range of other use cases, including supply chain management, identity verification, and voting systems. At its core, a blockchain is a digital ledger that records transactions in a secure and transparent way. Each block in the chain contains a record of one or more transactions, and once a block is added to the chain, the information it contains is considered to be permanent and unalterable. This creates a tamper-proof, permanent record of transactions that can be trusted by all parties involved. One of the key advantages of blockchain is its decentralized nature. Unlike traditional ledgers, which are maintained by a single central authority, blockchains are maintained by a network of participants, who each have a copy of the ledger. This creates a system that is resistant to tampering and hacking, as any changes to the ledger must be agreed upon by the network participants. Another key advantage of blockchain is its transparency. All participants in a blockchain network have access to the same information, allowing them to see the details of each transaction in real time. This can help to increase transparency and trust in a range of applications, from supply chain management, where it can be used to track the journey of a product from production to delivery, to voting systems, where it can be used to ensure that votes are counted accurately and transparently. One of the most important features of blockchain technology is its use of cryptography. Transactions on a blockchain are secured through the use of cryptographic signatures, which provide a unique digital identifier for each participant. This makes it possible to verify the identity of each participant in a transaction, and to ensure that only authorized participants are able to access the information in the ledger. However, despite its many advantages, blockchain is not without its challenges. One of the main challenges is scalability, as the number of participants in a blockchain network can have a significant impact on its performance. Additionally, there are concerns around the energy consumption associated with some forms of blockchain, particularly those that rely on proof-of-work consensus mechanisms. Another challenge is interoperability, as different blockchains have been developed for different use cases and applications, and they may not be compatible with each other. This can make it difficult for organizations to integrate different blockchains into their operations, and to move information and assets between different networks. In conclusion, blockchain is a decentralized, distributed ledger technology that enables secure, transparent, and tamper-proof transactions. It has the potential to transform a range of industries and applications, by increasing transparency, reducing the risk of fraud and tampering, and enabling secure and efficient transactions. However, there are also significant challenges associated with blockchain, including scalability, energy consumption, and interoperability, and it will be important to address these challenges as the technology continues to evolve and mature. The Internet of Things, IoT, refers to a network of physical devices, vehicles, buildings, and other items that are embedded with sensors, software, and connectivity, allowing them to collect and exchange data. The IoT is transforming the way we live and work, by enabling smart homes, connected healthcare, and industrial automation, among other applications. At its core, the IoT is about connecting devices and machines to the Internet, and to each other, so that they can share data and work together in new and innovative ways. This is made possible by a combination of advances in sensors, connectivity, and computing power, which are making it possible to embed Internet connectivity in a growing range of devices and systems. One of the key benefits of the IoT is the ability to collect and analyze large amounts of data from connected devices. This data can be used to gain insights into patterns of usage, performance, and behavior, allowing organizations to make informed decisions and improve their operations. For example, a smart home might use IoT sensors to collect data on energy usage, allowing the homeowner to optimize their usage and reduce costs. Another benefit of the IoT is the ability to automate processes and improve efficiency. By connecting devices and machines to the Internet, it is possible to automate many tasks and processes, reducing the need for human intervention and improving efficiency. For example, a smart city might use IoT sensors to automate traffic control and improve traffic flow, reducing congestion and improving safety. However, there are also significant challenges associated with the IoT, particularly around privacy and security. The large amount of data generated by connected devices and systems can be used to track individual behavior and activity, and this data can be misused for malicious purposes. Additionally, the security of IoT devices and systems is a major concern, as they are vulnerable to hacking and other forms of cyber attack. To address these challenges, there is a growing need for robust security and privacy standards for the IoT, to ensure that sensitive data is protected and that IoT devices and systems are secure. Additionally, there is a need for greater transparency and control over how data is collected and used, to ensure that individual privacy is respected. Despite these challenges, the IoT is a rapidly growing field, with significant investment from tech companies and governments around the world. As technology continues to advance and the cost of IoT devices continues to fall, it is likely that the IoT will become increasingly accessible and widely used, with applications in a growing number of industries and fields. In conclusion, the Internet of Things, IoT, represents a major transformation in the way we live and work, by enabling the connection of devices and machines to the Internet and to each other. By collecting and analyzing large amounts of data, the IoT has the potential to drive new insights and improve efficiency across a wide range of industries and applications. However, there are also significant challenges associated with the IoT, particularly around privacy and security, and it will be important to address these challenges as the technology
Quantum computers are a type of computing device that use the principles of quantum mechanics to perform calculations that are beyond the reach of classical computers. Unlike classical computers, which use bits to store and process information, quantum computers use quantum bits, or qubits. The basic idea of a qubit is that it can exist in multiple states at the same time, known as superposition. This means that a qubit can be in the state of 0 and 1 simultaneously, leading to an exponential increase in the number of possible states compared to classical bits. Another key quantum property is entanglement, where the state of one qubit is dependent on the state of another qubit. The combination of superposition and entanglement enables quantum computers to perform certain calculations much faster than classical computers. One of the most famous applications of quantum computers is Shor's algorithm, which can factor large numbers exponentially faster than the best classical algorithms. This has implications for cryptography, as many public key encryption algorithms rely on the difficulty of factoring large numbers. Quantum computers also use a different computing paradigm known as quantum parallelism, where many computations are performed simultaneously. This allows quantum computers to perform certain calculations much faster than classical computers. There are several approaches to building quantum computers, including superconducting circuits, trapped ions, and topological qubits. Each approach has its own strengths and weaknesses, and it is unclear which approach will become dominant in the long term. One of the challenges of building a quantum computer is that qubits are highly sensitive to their environment, and even small disturbances can cause errors in the computation. This is known as quantum decoherence, and it makes it difficult to maintain the coherence of the qubits for long enough to perform meaningful calculations. Despite these challenges, there has been significant progress in building practical quantum computers in recent years, and many companies and research institutions are investing in the development of this technology. While it is still early days for quantum computers, it is clear that they have the potential to transform many areas of science and technology, from cryptography and simulation to optimization and machine learning. Overall, quantum computers represent a radical departure from classical computing, and they have the potential to solve some of the most challenging problems in science and technology. However, significant technical and scientific challenges remain, and it will likely be many years before quantum computers become a widespread technology.